Okay, so at the end of the last video, we were on 18b, just about to get the wavelength, the de Broglie wavelength of the electron. So here it is, 3.3197 times 10 to the 10th. And then part C says compare it. Compare your answer to the radius of a hydrogen atom, which is 5.19 nanometers. So 5.19 times 10 to the negative 9th. So this guy is tinier. And when they say compare, they might want to know how many times tinier. So you could divide this one into the 5.19 nanometers. And if you do, you get pretty close to 16. So you would say it's like 1/16 of the radius of a hydrogen atom, which makes sense if you think it's an electron inside the hydrogen atom, so it should have a wavelength smaller than the hydrogen atom. Number 19, an electron has a de Broglie wavelength of 400 nanometers, the shortest wavelength of visible light. Find its velocity. So, see, I must have had a premonition when I was saying it must be time for them to make us rearrange that equation. So this time, they're telling us that lambda is 400 nanometers, and they're asking us nanometers, and they're asking us for v. So h over mv, you're going to rearrange it. So v is going to equal, I should have boxed that one up there, h over m lambda. So 6.626 to the negative 34 joule seconds. It's still an electron, so 9.109 to the negative 31, almost said 19 there, kilograms, and 400 nanometers, or 400 times 10 to the negative 9 meters. And when you do this, you get a speed of 1.818. 1.8185. It keeps going. 3 times 10 to the 3rd meters per second. Okay, so really, in a way, that's not all that fast for an electron. Lots of times we see electrons going to like the 5th. There is a B part that says calculate the energy of the electron in electron volts. So for part B, they're looking for EK, which is equal to 1/2 mv squared. So 1/2 9.109 to the negative 31 kilograms, 1.8185 to the 3 meters per second. Don't forget to square it. And when you do, you get an EK of 1.5062 times 10 to the negative 24 joules, but they wanted to know it in electron volts, so you're going to have to divide by 1.602 to the negative 19 joules per electron volt. And when you do, you get an EK of 9.402 to the negative 6 electron volts. So really, not a lot of energy. When it's even times 10 to the negative 6 in electron volts, you know it's small. Number 20 says, an electron microscope is useful because the de Broglie wavelength of electrons can be made smaller than the wavelength of visible light. When energy in electron volts has to be given to an electron, what energy in electron volts has to be given to an electron for it to have a de Broglie wavelength of 20 nanometers? So they're telling you the wavelength is 20 nanometers, and they're asking you for the energy in electron volts. It's identical to the previous question, they just didn't break it up into part A and part B. So first step, find V. Lambda equals h over mv, so V equals h over m lambda. 6.626 to the negative 34 joule seconds, divided, still an electron, 9.109 to the negative 31 kilograms, and 20 to the negative 9 meters. and you get a speed of 3.637. 6371 times 10 to the 4th meters per second. And so now you're going to find the kinetic energy equal to 1/2 mv squared. So 1/2 9.109 to the negative 31 kilograms, 3.6371 to the 4th squared. And in joules, you get an energy of 6.025 times 10 to the negative 22, I believe it is. If I can make out my own writing, it's too tiny. And you have to change that to electron volts by dividing by 1.602 to the negative 19 joules per electron volt. And when you do, you get an EK of 3.76 times 10 to the negative 3. 3.76 times 10 to the negative 3 electron volts. Your answer for 21 says, sorry, I'll read it in a second. I should write 21 here. Says, an electron has a de Broglie wavelength of 0.18 nanometers. How large a potential difference did it experience? Okay, so it has a wavelength of 0.18 nanometers, and this time it's looking for potential difference. Well, we know that if we have the kinetic energy, we can get the potential difference by V equals the EK over Q. So it's going to be all the same steps, just one additional in the end. So the first step, get your speed. So lambda equals h over mv. So v equals h over m lambda. So 6.626 to the negative 34 joule seconds divided by, it's still an electron, 9.109 to the negative 31 kilograms, and the wavelength 0.18 times 10 to the negative 9 meters. And so when you do this, you get a speed of 4.0412. 4.0412 times 10 to the 6th meters per second. Told you electrons could go fast. That okay. So that's the speed. So now we can get the kinetic energy. So EK is equal to 1/2 mv squared. So 1/2 9.109 to the negative 31 kilograms times this 4.0412 to the 6 meters per second squared. I'm just going to touch the paper to focus the camera. I guess if I touch the iPad, it'll work better. And when you do that, you get an EK of 7.438 to the negative 18 joules. I said 18 and wrote 19, but it really is 18. Okay? And so then, and it's a 1. I'll just make a total mess of the whole thing. So then V equals W over Q, or EK over Q. So 7.438 to the negative 18 joules divided by 1.602 to the negative 19 coulombs. And you get a V of 46.43 volts. Now, part B asks exactly the same thing except for proton. So the only thing that changes is where you have the mass of the electron, you're going to put in 1.673 to the negative 27 there and here. And when you do that, you end up getting a V of 2.528 to the negative 2 volts. And I did that because in 3 seconds, the video is going to end. Okay, so all you do is change the mass